All right. Welcome everyone to the Chemistry 3-4 Redox and Equilibria Autumn Lecture Series lecture. My name is Josh. I'll be your presenter today. Just a couple of things. Obviously, it's Chemistry 3-4 today. We're going to be covering a bit at the end of Area Study 1 for Unit 3 and then the start of Area Study 2. Given this is a recording, you'll find there is the live chat feature if you're here for the premiere. If not, you can still probably see that. I think you still can see the chat. The chat should be available afterwards. You won't be able to utilize the chat, but you'll be able to read through it. So if you have any questions, you should be able to see it there. Beyond that, I'm recording on my laptop, but my monitor has my screen. So if I'm looking up to my right all the time, that's what I'm doing. Other than that, we'll get started. So, obviously, a big welcome by ATAR Notes. Today couldn't be possible, or this recording couldn't be possible without ATAR Notes. They've been around for a very, very long time. I think it's about 2007, producing free resources. They even now have moved into some more high-end paid resources, but nonetheless, they've been around for a very long time. They've been supplying these lectures for a very, very long time. I remember going through high school and going to these lectures back when they sort of were a bit hybrid. There was some in person, some not. And so I did a bit of both, and I really enjoyed them back then. And now I'm lucky enough to be presenting them. Beyond that, just sort of what ATAR Notes offers. ATAR Notes obviously has a lot of free resources in terms of it has a big library on its website of sort of study notes that are available to download. There are these lectures such as this one here, discussions, their forums are really good. There's some video tutorials and some more resources there. They've also started to move into some more sort of high-end products such as ATAR Notes Plus. ATAR Notes Plus is essentially sort of a platform where you get access to all of the ATAR Notes books. So our ATAR Notes complete course notes and the ATAR Notes topic tests. You also get available, there's now flashcards. There's also now study guides for each of the texts, so text guides for each of the English texts. And there's now an AI answer bot who has essentially, it's an AI that's been taught in terms of the VCE books that we've produced. It's improved dramatically. I remember sort of seeing the beta of it at the end of last year, and it's sort of had a few little tinkering issues, but it's amazing now, and it's essentially, it's not as good as a tutor, being a tutor myself and tutoring through ATAR Notes, but it is very close and it's very, very good. So you get that all with ATAR Notes Plus, so it's definitely something to check out. There'll be some lectures on it throughout this lecture series, some sort of information videos. You're welcome to check those out and get in contact with sort of ATAR Notes if you have any questions in regards to that. But it's a really, really good program and definitely something to look at if you're looking for a little bit extra help. But what about today? So welcome to the Chemistry 3-4 lecture. We're in a new study design, so we're following on from the Unit 1-2 changes. Please feel free to utilize the chat to ask any questions if you're at the live premiere. The slides will be accessed below, so you'll be able to see the slides. They'll be below. So if you go to the chat and then scroll just below the chat, there's a couple of tabs. You'll be able to get the slides there. This recording will be available after the premiere. It's usually available for 7 days, and then it moves to ATAR Notes Plus. So if your friends couldn't make it today, make sure to tell them to watch it the next 7 days. Make sure they sign up to attend the live class, and even if they don't attend the live session, the premiere, even if they don't attend that, that's okay. Make sure they jump on and watch the recording afterwards. And then who am I? So my name's Josh. I'm sure you guys have seen me around before if you've been going to these lectures, maybe even last year. I've been lecturing these lectures for far too long. I graduated way back in 2018, and I'm now a final year medical student, so 6 years down the track. I've done completed an honours year, and I'm now a final year medical student. I work for TuteSmart by ATAR Notes, which is why I said tutoring is always better, because I'm a tutor at TuteSmart. I tutor Chemistry 3-4. I take the class there. I also have a couple of students individually, but that's sort of where I limit myself. But yes, that's what I do. I do also do a bit further and a little bit of biology. That's my main focus is really chemistry. It's where I really enjoy it. I enjoyed it in medicine and I definitely enjoy it at the VCE level as well. Essentially, that's who I am, and that's essentially why I'm here. So what we're going to do today, we're going to do a couple of things. So first of all, we're going to look at redox and electrolysis. So this is a bit of a culmination of Unit 3 Area Study 1 and Unit 3 Area Study 2. So these two are actually split up in the study design. So if you get up the study design, you'll find that redox makes up the back end of Area Study 1, just basic redox in cells. And then electrolysis makes up the back end of Area Study 2. And it's a little bit frustrating because most schools I find, and including my school, make that one SAC, even though the area studies are different. It's a bit frustrating, to be honest, but nonetheless, for today, I'm going to combine the two. They lead on from each other. They make sense. There's no point doing it separately. And then we're going to touch on equilibrii. Now, we're not going to go through all of equilibrii, nor are we going to go through all of electrolysis. So I really want to sort of stamp out today that the reality is in 2 hours, we can't go through everything. We're going to go through redox, and we're going to go through all of what is in Area Study 1. So you'll find that all of Area Study 1 redox is covered. So you should have already probably done that in class by now, given it's now the school holidays. So you should probably be at the stage of saying, hey, I've already done this, so this is good revision. And you should have probably just started equilibrii. Or if you were like me and you did redox and electrolysis in one, you may have just finished electrolysis, maybe in the middle of electrolysis. That's usually where people are at this point of the year. Now, if you are like me and you're just into electrolysis, then we'll cover probably what you've done and a little bit more, which is good. If you've just started equilibrii, we're going to cover what you've done and a little bit more. But we're not going to finish all of electrolysis and all of equilibrii. We'll sort of briefly go over most of electrolysis and majority of equilibrii, but not in super detail, more on the basis that you cannot go over it in a 2-hour lecture. There's not enough time for that. So I just want to give a very sort of brief glacé overview of it, essentially. And that's sort of how we go about it. Now, how's today going to work? 80 minutes on redox and electrolysis, or essentially about 75 because including this intro, and then 40 minutes on equilibrii. So just as a quick thing, I show these in each of my lectures. Make sure you understand how the study design works. It goes from fuels to electrochemistry to rates and equilibrii. Now, electrochemistry, again, is sort of broken up into the two. The first part that's on the back end of fuels and the second part's on the back end of rates and equilibrii. I've sort of just combined them here. And then Unit 4, which has experimental design, organic chemistry, and analytical chemistry. It's really important you understand how this workup goes, how we go from one to the other, and how they sort of build upon each other. And it's really important that you have read through the study design at this point. You have sort of either printed it off or you have it available somewhere so that you can sort of not jot down little points as you go through the year. And you know what you're sort of missing or what you're not missing, essentially. So let's jump into redox now. And we're really going to start off with the basics. So what you're going to find is we're really going to cover the basics of redox. The reality is, and I'm going to preface this, that I personally still think, despite the fact I've tutored chemistry now for 6 years, and I believe my knowledge is probably greater than what it was. It's definitely greater than what it was when I went through year 12. I still believe redox chemistry is probably the most difficult topic in 3-4 chemistry. I think the breadth of which they can ask questions is the most. There can be more difficult questions on the background of this. And I also believe that at times, redox chemistry is planted in the basics. And if you don't know your basics well, you'll really struggle to maintain your knowledge. So I'm a big believer that our redox chemistry really importantly needs to be strong. You need to know your redox chemistry really well, and you need to know your redox basics well to know your redox chemistry well. So, moving forward, redox and oxidation. Redox is made up of reduction and oxidation, and so we know that oxidation involves a loss of electrons, reduction involves a gain of electrons. It's good to know the acronym oil rig. Oxidation involves loss, reduction involves gain, and therefore you get your acronym of oil rig. It's good to know sort of your basic structure of half equations. So I use M as like molecule. Molecule goes to molecule ion plus electron, and that gives you sort of oxidation. Whereas reduction is the opposite. You get your molecule ion plus your electron goes to your molecule. So oil rig is your acronym. In a redox reaction, one species is the oxidant and the other is the reductant. That's really important to understand. And the terminology is super important. Now, I don't want to harp on about this because I feel like sometimes the more you talk about this, the more you confuse yourself. But it's important to understand that the oxidant itself is reduced, but causes oxidation of the other species, much like how a teacher does the teaching. Again, the same thing, the reductant causes reduction, and therefore it itself is oxidized. You cannot have one without the other, that's super duper important, but the oxidant causes oxidation, the reductant causes reduction. So in the other way that you can sort of think about it is the teacher does the teaching, doesn't get taught themselves, they do the teaching, just like the oxidant does the oxidizing. So essentially the oxidant causes something else to be oxidized, but it itself is reduced. And that's a really important sort of distinction you need to be able to make when going through this stuff. I'm just getting a good pen color so we can sort of do some drawing as we go through. All right. Redox reactions, importantly, cannot happen without both. So you cannot have oxidation without reduction, and you cannot have reduction without oxidation. That is the reality of this situation. One must happen without the other. You cannot separate them. Electrons cannot be lost, nor can they be gained. They must be conserved. It's much like the idea of energy for those who do physics, and again, this is in chemistry as well. But the idea of energy is never lost, it is just transformed. We talk about this in chemistry, we talk about it more in physics, but it's an important idea. So same thing with electrons. Energy or electrons cannot be lost or randomly gained, they must be transferred. So then I say to you, all right, well, if I provide you with 3 different equations, and I've provided you with 3 different equations here, which of these is a redox equation? And unlike in a diagram that you sort of saw before with like the oil rig and the different equations, you can't explicitly tell you where is the electron movement, what is going on. You can't look at those half equations that I showed you before. So in this case here, we have to use oxidation numbers, or what sometimes the exam will refer to as oxidation states, to determine if the equation is redox or not. So there's a few rules to remember, and you need to feel comfortable with these. So the first rule here is the idea that oxidation states of free elements are always 0. So as you can see here, your oxidation states of Fe solid, your Na solid, your Cl2 gas, they're going to be 0. Your oxidation states of simple ions are always going to be whatever the ion is, the charge of the ion. So +1 for sodium, -1 for chlorine, magnesium's +2, etc. In compounds, there's a few different rules. So in compounds, it's really important to understand that the main group ions, or the main group metals, and the ions of those metals are usually what takes precedence. So the metals are usually at the front. So if we look at something like sodium chloride, the sodium is the metal, therefore the sodium is going to keep the +1. So as you can see here, this is the +1 here. Now, if you have your magnesium, you're going to have your +2. Therefore, from there, you sort of work off everything else. So as you can see, sodium chloride here, it has an overall charge of neutral, 0. Therefore, the chlorine is going to be a -1. So you'd put a -1 above the chlorine. Now, on the other hand, you've got magnesium bromide. There's 2 bromides there. So therefore, they're actually going to be -1 each. But you're going to have 2 of them because they're overall going to cause a charge of 0 over here. And that's essentially how that's working there. Now, hydrogen is almost always +1. Oxygen is almost always -2. The only example I want you to know where one of those is not what it says there is oxygen in hydrogen peroxide. Hydrogen peroxide is H2O2. Hydrogen peroxide is, I don't know if you've seen maybe you've seen movies, especially like wartime movies. Hydrogen peroxide is what they used to use as sort of a poison. And hydrogen peroxide is essentially a very deadly poison. And I think we still use it in some cleaning products, and we still use it in some pesticide poisons, etc. But essentially, hydrogen peroxide is a very unstable molecule because the oxygen is -1. So you've got 2 hydrogens, which are +1 and +1, and then you've got an oxygen, or 2 oxygens actually, that are -1, -1. So it's the only example I want you to know. It's come up in the VCAR exam a couple of times. Last time was probably 3-4 years ago. But it's still something that could likely come up, so good to know. H2O2 is the only time you need to know oxygen is something else. Hydrogen, anything other than +1 has not really come up on an exam for about 20 years, so I wouldn't worry about it too much. Hydrogen is always +1. The next and last rule is the sum of all oxidation states must equal the charge in the species. So we've already talked about this in like sodium chloride there. It had to be 0, so +1, -1. So in these cases here, you need to work through them. So I put all three cases here because I think they're really good examples, and so you can have a look at sort of where you determine what's going on. So in our first one here, in your carbon dioxide, you'd work off your oxygen first, which is -2, because we know that oxygen is always -2 unless it's hydrogen peroxide. So here your oxygen is -2, you therefore have sort of -4. So therefore to get 0, you need +4 as your carbon. Again, here you've got oxygen again, -2, you've got 4 of them, so you've got sort of -8. You need to get to -3, so what's the difference between those two? Well, it's +5. And then over here, well, you know what each of these are, so you can sort of work it out that it's going to be +1. There's no real sort of hard work going on there to determine that. It's all pretty sort of straightforward stuff. All right, so continuing on, this is our example from before. So I had three different examples here, and I say which of these is redox. So you should be able to determine pretty quickly which of these is redox. And the best way to do this is to look at, man, this is always my first inkling, and it's why it's the first rule. Which of these has an oxidation state of a free element? If you look at the 3 of these, there's no free elements here, there's no free elements here, there are 2 free elements here. So given that there are free elements, it's more likely it's going to be redox. It doesn't say there will be, it doesn't mean there will be, but it's more likely. So therefore, I'd look at these and go, all right, there is a change, because these are now in a molecule, and in a molecule, they sort of act like ions. This is +3, this is -1. Therefore, there is a change. The aluminium here has gone from 0 to +3. That means it has lost electrons. It has gone through oxidation. The chlorine gas has become chlorine ions, essentially in a molecule or in a compound. And this chlorine gas was an oxidation state of 0, and now it's an oxidation state of -1. So it has gained 1 electron each, and therefore we call this reduction. So non-oxidant, not redox, not redox, redox. So if the oxidation state reduces, then the species was reduced. So Cl goes from 0 to -1. If the oxidation state was increased, then it would be oxidized. Now, question to everyone who's watching this, and have a think. There's no way of you really to respond to me. What's going on here in terms of the reductant and the oxidant? So take a second, have a think. What do you think? Well, I would sort of think of it like this. The aluminium has essentially been oxidized. Therefore, it has caused reduction of the Cl2. So therefore, this is the reductant. The chlorine has gone through reduction and has caused oxidation of the aluminium. Therefore, this is the oxidant. So the chlorine gas is the oxidant, the aluminium solid is the reductant. That's the best way to go about it. So now we understand that. The next sort of basic step is formulating half equations. So you should have sort of been through this in Unit 1, 2, but we're going to go through it again. Sometimes you'll be asked to create half equations. And when you are asked to create a half equation and it's not in your electrochemical series, which will be on your data booklet, which at the time of recording this, you still don't have your new data booklet. So just for the information, just so everyone is on the same page, for this year, and so for this new study design that's covering 2024 to 2027, there should be a new data booklet. It is currently not released at the time of recording this. So utilize the old data booklet where you can. The old data booklet has everything you need. It does not lack any information that the new study design has. There's just irrelevant stuff on it now that will get removed. Essentially, the old data booklet is perfectly fine, has everything you need. Now, if you go to the electrochemical series on that data booklet, it doesn't have everything. And sometimes you need to create half equations that are not on there. And therefore, you need to use a method called COES. Now, this COES method works pretty straightforward. You have your pairing. So you have, let's just say, you're going from dichromate to chromide ions. It's a very common example VCAR likes to use. So that would be like Cr2O7 -2 to Cr3 plus ions. Now, it's a very, very common example. VCAR loves this example. You work with that example, and you would, first of all, you'd put those two on the page and draw an arrow and leave a bit of a space after. So you write the dichromate, leave a bit of space, arrow, chromite ions, a little bit of space. Those spaces you need to fill in. Essentially, you'll go through this method. You'll first of all balance your key atoms. Now, that would start off with the dichromate. So it would start off with the chromide in there, or the chromium that's in there. So the chromate ions and the dichromate, you'd need to sort of alter their sort of coefficients to ensure that the chromate ions are balanced. Don't worry about the oxygens yet. You then balance the oxygens, but you don't balance the oxygens by changing coefficients. You balance the oxygens by adding H2Os to the side with less oxygens. So you balance that out by adding H2Os. You then balance the hydrogens, which you probably threw out of whack by adding in H2Os, by adding H plus ions to the opposite side, or the side that has less hydrogen. So that's how you balance it out. Now you will have probably thrown the charge out of whack because these have a charge. So then you need to add electrons. Now, if you've been told that you are going to draw a reduction half equation, you should know that reduction involves gain. You should know the electrons need to be on the left. So if you are asked to write a reduction equation or a reduction half equation, and you are given the two starting molecules or compounds, whatever they are, and you put it all on your page, and for some reason your electrons are not on the left side, they actually end up on the right side, you've done something wrong. So that's a good sort of hint to you to go, I've done something wrong. I need to take a step back and redo everything else that I've done. And that's reasonable. And that's why it's important to know that reduction is on, like, the electrons are always on the left, and then in oxidation, your electrons are always on the right. It's good stuff to know so you can sort of fact check yourself as you're going through. So as you can see here, you balance the charges by adding the electrons, and then don't forget the states. So add states last. So add all your states in last and make sure you don't forget them. That's like completeness sake. In an exam, you're not going to get marks if you don't put states. You have to put states down. Really important. So your Coe's method is really useful. The only issue with your Coe's method is that we make an assumption that the medium is acidic. Now, I want you to take a think, why do I assume using this method that the medium is acidic? Well, it's this step here. This step here assumes acidity. Why? Because H plus ions are acidic. They're just naturally very, very acidic. They are essentially what we measure in pH. You will have learned that in Unit 1 too. But H plus ions are really our measure of pH because they're protons. It's what we work with. Now, because we assume we are acidic, or we are told we are in an acidic environment, we use Coes. Now, what happens if in the question it says that the medium is basic? Now, this would only be if the question mentions it. If the question mentions nothing and wants you to form a half equation, you assume acidity. You assume that the medium is acidic, or like, slightly acidic. It doesn't need to be super acidic, but that is an assumption you make. The only time you will use this second method I'm about to go through is if you are told in the question you are in a basic environment, you're in an alkaline environment. That is the only time you will use this. And in this one, you use the exact same method with an extra step. There is one extra step added in. And that extra step is after these hydrogens. So after you've added the hydrogens in and you've added these H pluses, you don't want them. You want to get rid of them, but you've got them there. So how do I get rid of them? Well, the best way to get rid of them is make them into something else. So you add OH ions, the same number of OH ions as there are H pluses, and you add them to both sides. Now, the OH ions on the side with the hydrogens, let's say the hydrogens are on the left side of the equation. You add OH ions to the left side of the equation. There were 4 hydrogens, so you add 4 OH ions. What does that make? It makes 4 H2Os. You combine them and make 4 H2Os. But you only added hydrogens to the left side of the equation because there was water on the right side of the equation that had increased your hydrogens. Well, now you need to cancel. So you do some cancelling. There might be less water on the right than what there is on the left. So now you cancel out the ones on the right and you make your coefficient of your waters on the left a little bit less. So you cancel out your waters accordingly. And then you add your 4 OH ions to the right side as well. Because you added 4 to the left, you must add them to the right. You're not balancing at this point, so you can't just add one or the other. You need to make sure that you cancel out appropriately, and then you make sure that you balance appropriately in terms of if you've added 4 to the left, you must add 4 to the right. That is an important step. You are not balancing out oxygens. You're not balancing out hydrogens. You're not doing that anymore. You're essentially trying to cancel something out. So by trying to cancel something out, you need to add to both sides, left and right. So really important here, this is only a method, this COES with a double H, is the only time you would use this method is if you are told it is a basic or alkaline environment, and that is super duper important. Everything else is the same, it's just this extra step of adding OH ions. They will combine with the H pluses to form water, and when they combine with the H pluses to form water, that's what you get. So from here, we need to sort of then talk about, well, what is actually going on in redox? So what's going on in redox is we're transferring electrons, but what we do by transferring electrons is we essentially transfer energy. And what's really important is that when we transfer energy and we do it all in one beaker, we call this a direct reaction. And really, unfortunately, with a direct reaction, they're really easy to do, but they're really useless. You get chemical energy to thermal energy, which is not something that we sort of want. Chemical energy to thermal energy is a bit useless in our eyes. We don't really like chemical energy to thermal energy. Thermal energy is hard to work with, and we don't find it useful in everyday life. However, we can use cells. And the use of cells is essentially that we can get chemical energy and we can convert it into electrical energy. So we can take the chemical energy and we can convert it into electrical energy. So electricity is much easier to store and control, and thus much more useful. And redox is essentially the transfer of electrons. So if we force those electrons through a wire, instead of allowing them to directly react in that sort of direct singular environment, instead of allowing that transfer to happen in a single environment, we can sort of force it to happen through a wire. We can sort of connect things with wires and say, hey, react. But hey, the only way you can do it is if you send your electrons through this wire. By sending the electrons through the wire, we essentially get electrical energy. That's how current forms, that's how voltage forms, and that's how we get electricity. And this process occurs in what we call galvanic cells. And as I said, it produces electricity. Now, I hope you know what galvanic cells are by now. I hope you know how to draw one. If you don't, or if your galvanic cells don't look slightly like what I draw, do what I'm doing. So this is what your galvanic cell drawings should look somewhat like. If they don't look somewhat like this, then you need to start drawing them like this. This is a basic galvanic cell. What's really important about a galvanic cell is that it has two electrodes. It has an external circuit. It has two solutions, or two beakers, and it has a salt bridge. They are the most important steps and the most important things you must have in your galvanic cell. Now, yes, galvanic cells will slightly change depending on what you're putting in there. So if you're putting in like a gaseous electrode or a porous electrode, you're going to have some differences here and there, and that's normal. We're not opposed to that. But it's super important that you understand that the galvanic cell drawing must have these basic things in there, and that's important. Now, what's also really important is that a cell does not make up a full battery. As much as that cell there looks like a battery is the whole bunch of cells. So a singular cell is not going to be strong enough to power pretty much stuff off. You're not going to get anything powered by a singular cell. Lots of cells together are going to power lots of things, and they're going to produce lots of power and enough to, use your phone, use your laptop, electrical vehicle, etc., all those things. So really important that if you want to form a battery, you need multiple cells. You cannot get away with forming a battery from just one cell. It doesn't really work like that unless you're working with maybe like a fuel cell, and they do produce a fair bit of energy, but even then, it's probably not going to be enough. You need multiple cells to form a battery. It's a really important idea to get your head around. So let's look at this example now. So we're going to use a very basic example, and that basic example is zinc and copper. So if you looked at your electrochemical series right now, so I hope you probably all either have a link up with your electrochemical series, or not your electrochemical series, your data booklet, or you've got your data booklet in front of you. If you don't, you need 5 seconds now to get it up. Search up VCAR data booklet, and it should come up. I can literally go across, and I have mine up here. So I've got my data booklet up here, just on another page which you cannot see. So with my data booklet up, I know that electrochemical series is on page 4, and given that the electrochemical series is on page 4, I know that I know that zinc and copper will react. I know that zinc solid is, if I go to my book, I can see that zinc solid sits at about, where am I? I think I've lost it. I had it in my eye before. There we go. Zinc solid sits on the right side of the equation, and it's at negative 0.76. Copper 2 plus is on the left side of the equation. It's at plus 0.34. So I know these are going to spontaneously react. And that is the reason why, in this case here, I've got zinc on the left. I've got zinc solid and copper 2 plus as my reactants. I understand that the zinc, from looking at my electrochemical series, I understand that zinc is going to go through oxidation because it's going to lose electrons. It's going to go to 2 plus. I know that copper is going to gain electrons and therefore go through reduction. Therefore, I can say, all right, I can say zinc occurs at the anode because the anode is the site of oxidation. Vowel to vowel, A to O, vowel to vowel, anode to oxidation. That is the best way to remember it. It is negative. In our spontaneous redox, it is negative, and that's super important to understand as well. We then, therefore, know that there's zinc 2 plus in that solution. It's aqueous. On the other side, we have the cathode. Now, the cathode is positive, so the cathode is the happy cat. It's positive. So given that the cathode is positive and we have a copper solid electrode that is positive, that's what's going to happen there. We know that copper is in the solution. We also understand that the electron flow is always anode to cathode. I hope you know that by now, but it is always, always, always anode to cathode. And the salt bridge is made up of KNO3. Now, you might have been told something else, that's okay, but KNO3 is always the one that I use. Really important, the cations, so the K plus goes towards the cathode, the anions, the NO3 minus goes towards the anode. The anode will slowly form more Zn2 plus, and the Zn will be used up as the electrons flow to the cathode, and you get more copper solid formed. And that is a very basic galvanic cell. That is essentially the most basic galvanic cell you can work with. So as you can see here, this is your electrochemical series. Your electrochemical series can show you your strongest oxidant, your weakest oxidant, and increasing oxidant strength. It can also show you your weakest reductant, your strongest reductant, and increasing reductant strength. So from now, you can sort of change what you say as your sort of acronym. You can say, instead of oil rig, you can say an oil rig cat. An oil rig cat, and the cat is always happy. That's how I sort of think about it. So as you can see here, the anode is the side of oxidation, the anode is negative. The cathode is the side of reduction, the cathode is positive. The anode is defined as the site at which oxidation occurs, and the cathode is the site at which reduction occurs. We do not call something the anode or cathode unless reduction is occurring. If a reduction is not occurring, redox is not occurring. If redox is not occurring, we call it an electrode. Once redox starts occurring, we can call it the anode or cathode. We can't just say, hey, that's going to be an anode, or that's an anode. It's not an anode unless oxidation is actively occurring at that site. Otherwise, it's just an electrode. It's a really important sort of distinguishing feature. So now we've seen the sort of following reaction in a galvanic cell. What about if I did Mg2 plus instead of Cu2 plus? Well, the answer would be no. We wouldn't get a reaction occurring. Now, why would I not be getting this reaction occurring? And that's because of our spontaneous reactions. So we understand top left, bottom right, copper 2 plus goes to Zn2 plus. But what about magnesium 2 plus? Well, magnesium 2 plus to Zn2 plus would actually have to be a forced reaction. It would have to be an electrolytic reaction, and therefore we call this non-spontaneous, and redox would not spontaneously occur in this situation here. So if the oxidant on the left-hand side is above the reductant on the right-hand side, we will spontaneously react. If we're not, then we won't get spontaneous reaction. So the other important fact is understanding how the electrochemical series was created. And the idea that the electrochemical series was created in a stable environment. Now, the electrochemical series was made by comparing all of our other half cells with the standard hydrogen half cell, which is found at 0 volts. And that's why we refer to the standard hydrogen cell as 0 volts. Because if we connected the hydrogen half cell to the other hydrogen half cell, we got 0 voltage. because they're not going, nothing's going to happen. So therefore, that was referred to as 0. Everything else, we measured the voltage, and we sort of, from there, determined where they occurred on our electrochemical series and slotted them in and made our essentially electrochemical series. So this all occurred at SLC. I hope you know SLC conditions by now. It should have been part of your sort of gases in area study 1, but nonetheless, it's your 25 degrees Celsius, 298 Kelvin, your 1 molar aqueous solution, or your 100 kilopascals. So they're your features of SLC. This is definitely a limitation of the table. The issue with the table is that when you go through redox, even if it is indirect, you are going to get a little bit of temperature change. That's the reality of it, and therefore it's never 100% accurate. You're never going to get 100% the exact same thing going on, because you can never really guarantee you're at 25 degrees Celsius. But it is important to understand if you're working with a gas, it's at 100 kilopascals, or if you're working with a solution, it has to be 1 molar. It's really, really important. So as you can see here, this is sort of what they did. They got the hydrogen half cell here, here, and here. They utilized it 3 different times here. They, first of all, compared it with zinc. So a zinc half cell, which had a zinc 2+ solution and a zinc electrode. Here they compared it with PB, so they had a PB solution and a PB solid electrode. And then here they compared it with silver. So they had a silver electrode and a silver solution. So as you can see here, the zinc went from left to right, which meant that the zinc was an anode, and it told you that the Zn2 plus was a weaker oxidant than H2 plus. No, sorry, H plus, not H2 plus, 2H plus, not H plus. So H plus is a stronger oxidant than Zn2 plus. Zn2 plus is weaker. Then we had our lead, and we determined that our lead 2 plus is also a weaker oxidant than our H plus. But it's not as weak as our Zn2 plus. Why? Because there was a much smaller potential difference, or a much smaller voltage than this one here. This determined that there is a much bigger gap going on. But then on the other hand, when we put in our silver, we went the other way, where our voltage went the other way. And we found that electrons were going from the hydrogen half cell to the silver, rather than towards the hydrogen half cell on the other two. So what you can determine there is that Ag plus is actually a stronger oxidant than H plus. So H plus is actually below it on the table. And that's how we determined this here. And we noted that this is quite a big voltage because there's quite a significant difference between the two. And as you can see there, strongest oxidant, and then you would have this, and then you would have this. So what if there were multiple reactions? So what if I had a beaker that had multiple different things going on? You need to understand that there's going to be preferential oxidation and reduction. And the way that you determine that is always by picking the strongest oxidant and the strongest reductant. So highest on the left, lowest on the right. Pretty simple sort of rule, but you do need to stick to it. So highest on the left, lowest on the right. Always pick your strongest, and that's what you go with from there. And then how to determine your potential difference. Your potential difference, or your E0 value of your cell. So E0 is that E with that little O at the top. So E0 essentially means, well, what is the potential difference? What is the voltage if I connected a voltmeter between the two half cells? Essentially, as you can see here, that your E0 value should always be positive. Now, why is that? That's because you're always going to take your smaller value from your bigger value. So your bigger value always goes first. So the one that's at the top always goes first. Now, you might say to me, well, what if I had 0.15 and then I had negative 0.28? Well, this number, like, wouldn't that form a positive? Well, no, it wouldn't, because if you take a negative from a negative, you're going to add it. So pretty sort of simple math stuff just to determine that you should always get a positive voltage out of this. If you don't get a positive voltage out of this equation, you've done something wrong, you need to redo it. It's really, really important to understand that in this equation, you should always get a positive voltage. All right, and then fuel cells are sort of the next step on. So we've looked at galvanic cells. Now, what about fuel cells? Now, fuel cells are a very specific type of galvanic cell. They still have half cells, they still have electrodes, they still have an external circuit, they still convert chemical energy to electrical energy. So they still do all those features. However, unlike traditional galvanic cells, you do not run out of charge. They need to be they do not need to be recharged. They need to have a consistent supply of, or a constant supply, or a continuous supply of reactants. They must always have reactants going in. As soon as reactants stop going in, the fuel cell kind of falls apart and stops working. So, one of the more common examples of a fuel cell is the hydrogen fuel cell. It's actually explicitly mentioned in the dot points now. You do need to know this. You do also need to know industrial examples of fuel cells now. It's not something that I think I discuss in super detail today, or even at all. No, I don't actually discuss it at all. But you need to know your hydrogen fuel cell, and you need to know a commercial example of a fuel cell. The most common one is usually like the methane one. It's like the DCMF or DCM. I think it's the DCMF. That is the most common example of a methane fuel cell that is used in commercial levels. So it's one that you do need to know, and one that you do need to be able to apply. But nonetheless, jumping back into this, as you can see here, when we work with our hydrogen fuel cells, we get this example here. Now, this example here is a very good sort of diagram showing what happens when you get the fuel going in. You get this hydrogen fuel going in, so hydrogen gas, it goes in. These electrodes would need to be porous because you would need to be allowing the hydrogen into the electrode. And then instead of having a salt bridge, or instead of having like separate beakers, you've got an electrolyte separating these two. So they cannot directly react. There needs to be some movement of ions though. And this H+, once it's broken apart and the electrons move off, the H+ has the ability to move across this electrode, or this electrolyte. And as it moves across this electrolyte, it reacts with O2 that's been broken apart by these electrons, and it forms H2O. So in goes O2, out goes H2O, in goes H2 gas, out comes any excess gas that didn't react, but nothing else comes out on this side. So as you can see, your oxidation reaction is H2 goes to H+, and your reduction equation is O2 goes to H2O. So what's your overall equation here? Well, it's H2 plus O2 goes to H2O. Very sort of straightforward overall equation, and one that's really, really sort of easy to use and easy to work with in sort of chemistry. You'll find that this one comes up a lot, and one of the more straightforward ones to work with, and it's a good example of a fuel cell to go through and know well when it comes to the exam. So beyond this, it's also useful to know this is sort of how it works. As you can see here, this is a really good way of visualizing it. It's a GIF, whatever you want to call it, but they're really useful. So you can search these up online, and they're available online to look at, and they're really, really useful to use, really useful to learn off. So, as we said, galvanic versus fuel, main difference, continuous supply, whereas galvanic cells don't really need that. If you're asked on an exam for a difference, you always go to this first. However, there are a few other subtle differences if you really want to talk about it, like the properties of electrodes, the operating temperatures, the role of the electrolyte, what they're used for, etc. So there are a few subtle differences. And then what are the advantages and disadvantages? This is another really common thing that comes up in our fuel cell discussions, particularly in exams. They love to bring up, hey, if fuel cells, what's so good about fuel cells? Why are we using them everywhere? And you need to be able to discuss, like, what are the advantages? What are the disadvantages? What is stopping us from using fuel cells everywhere? What is, allowing us to use fuel cells more? Like, discussing those features is super duper important. So as you can see here, fuel cells have a really high energy efficiency. And as I tried to briefly discuss earlier, fuel cells get a lot more energy or usable energy out of a fuel. They're something like 80% efficient, I think. I don't know the exact value off the top of my head, but they're very, very efficient compared to what general combustion is. Really important point with that is that why wouldn't we then use fuel cells all the time? Well, it's this idea that they are really expensive to produce. They're really expensive to upkeep. So usually they're pretty reliable. They don't need a lot of work, but when something wrong does happen, they're really complex pieces of machinery and they're really hard to fix. And the storage of our primary fuel is just really difficult, particularly in hydrogen fuel cells. It's really hard to store our hydrogen fuel. Now, fuel cells work a lot better when it's a gas as well. And generally our gas fuels are not that sustainable, nor are they that energy product, like they don't produce that much energy as is. Particularly even if you are more efficient, you're not really getting that much more. So again, it's sort of all those common sense sort of disadvantages that stop us from really utilizing what fuel cells could give us. But as you can see there, this is a really good slide for giving advantages and disadvantages. And then something I discussed in the last lecture, so if you haven't seen, I discussed this in the earlier lecture at the start of this year, was that this idea that green chemistry principles are now sort of sprinkled throughout our chemistry 3-4 study design. And this is one of the examples I explicitly want you to know. And that's the idea of what are the green chemistry principles that apply to fuel cells. So I've sort of discussed 3 of them that I believe apply here. So things like catalysts, design for energy efficiency, and use of renewable feedstock. You can have a read through these if you'd like, but these are just suggestions of how you would go about discussing the green chemistry principles in terms of fuel cells. They're not set in stone, and they're not the answer you must give in an exam. This is what comes up. These are just what I suggest and what I think would be appropriate answers in this case, and how you would relate them to hydrogen fuel cells. All right, so let's jump on to electrolysis. So we've been through about 40 minutes of redox. We're going to go through about 30 to 35, maybe more like 30 minutes of electrolysis. And then what we'll do is we'll jump into equilibria. If you need to take a break, feel free to pause and come back. Otherwise, I'm going to jump straight into electrolysis. I'll probably take a break, so you see a little cut in between electrolysis and equilibria. But that's these slides here, essentially here, if you want to take a break, quickly pause and then come back. So let's talk about electrolysis. So electrolysis is essentially where we sort of reverse redox. We do the opposite. So consider the following chemical equation here. We've got solid sodium and we've got chlorine gas. This is a spontaneous, highly exothermic reaction. It's a really, really dangerous reaction. It's actually not very safe, but it's a really spontaneous reaction. So if you put these two things in the same environment, you will get NaCl. Now, what if we had NaCl and we wanted to separate it back? Now, NaCl is really common. It's just table salt. It's everywhere. How do I convert it back into these two products? This, for a very, very long time, was impossible. We never knew how to do this. For a very long time, we sat there and went, I don't think this is possible. I don't think there's a way to do this. We know how to obviously create it, but to go the other way is just way too hard, and it's far too dangerous. And it's an issue we had for a very, as I said, a very, 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 very long time. But now we know how to do it, and we do it through what we refer to as electrolysis. Now, electrolysis involves the supply of electrical energy through a conducting liquid. So this causes redox reactions that are non-spontaneous to occur. As the reactants don't typically react, they can be placed in the same cell because we're not worried about them reacting with each other. So they're not going to spontaneously react. They're not going to get a direct reaction. So we can just chuck them in the same cell and just leave them there for a bit. And then we can force them to react. And by forcing them to react, we get what we want. So think of this as the opposite to galvanic cells. So we have chemical energy to electrical energy. That is our galvanic cells. We're now going to convert electrical energy back into chemical energy. That's electrolytic cells. So this is a very common example of what an electrolytic cell looks like. You have your electrolyte, which can be aqueous or molten. Doesn't really matter what it is, but that's got everything in it. You've got an anode and you've got a cathode. From here, you supply some power. Now, really important, the negative side of power has electrons going towards it, or going towards the negative side. Positive side has electrons coming away from it, essentially. In terms of, like, this is your positive side, you've got electrons going that way to your negative side. Now, what's really important here is everything is essentially flipped. The anode becomes positive, the cathode becomes negative. So the cat doesn't like electrolysis, cats don't like electricity, therefore it is negative. That's sort of how I think about it. So cathode becomes negative, anode becomes positive. Notice how electrons are still going anode to cathode. Electrons will always go anode to cathode, that does not change. Now, electrolysis, despite being non-spontaneous and top right, bottom left, and that's something that we will talk about, it'll use top right, bottom left, we will still use the strongest oxidant and the strongest reductant. So no matter what, we are going to use the strongest reductant and the strongest oxidant. That is just the reality of this situation. We will always still utilize them. So it is important to understand that despite being described as the opposite of standard redox, the electrolysis still follows many of the standard rules. These include the anode is the side of oxidation, the cathode is the side of reduction, and that the electrons flow from anode to cathode. So all of these rules still apply. There's no change to these rules at all. So it's important you sort of stick with these and don't change these up. But there are some distinct differences, and that's super important to understand as well. The most important is that the involved species are found top right and bottom left, or next to each other. The anode is now positive, the cathode is now negative. So here's a really good table. You're welcome to come back to this and look at it whenever you would like. It's available here on the slides. You can take a screenshot of it if you would like. It's got galvanic and your electrolytic processes and what are the differences between the two. I'm not going to go through it, but you're welcome to utilize it. So remember this example from earlier. In this example, we discussed that if magnesium 2+ and Zn solid were placed in a cell setting, no reaction would occur. So we talked about this a little while back, 20 minutes ago. And I said, hey, you're not going to get a reaction here. So these two here, you're not going to get a reaction. It's not going to happen. However, in electrolysis, this is different. Given our electrolytic cells are not separated, if I placed Mg2+ and Zn in together, nothing would happen until I apply power, and that's exactly what we want. But once this begins to run, Mg solid and Zn2+ form, which would lead to spontaneous reaction back. So that is direct in nature. So what I'm trying to say here is that if I had a beaker, so if I get my rubber out, I want to get rid of that, where's my eraser? I want an eraser. So if I said to you that I put one beaker, I get one beaker, and I fill it with Zn solid, and what's a different green? That's okay. And Mg2+. Nothing happens. I then apply some electricity, and I go through electrolysis, and they flip over, and I get Zn2+ forming, and I get Mg solid forming. I now have a spontaneous reaction possible. They are still in the same beaker. So what's going to happen? I'm going to get a direct reaction. I'm going to get heat energy, and it's not going to be useful. So despite this, we still have to sort of somehow separate these, and we still have to work out how we're going to change what's going on. And it's important because secondary cells are really complex like that. So secondary cells are super complex. Sometimes they're in the same beaker, sometimes they are not. And it's determining what is going to be produced and where it's produced as to what is going to happen. So electrolytic cells are quite difficult to work with, and so we'll discuss that as we go through. But if we consider a mixture here, and we have all of these things, and if I look at this electrochemical series, I say, hey, what's going to react? So I apply some electricity, and I have all of these things present. Well, what's important is I'm going to have these two here react. No, sorry, yeah, these two here, because this is the strongest oxidant, and this is the strongest reductant. Now, the only reason this was present was because these were all aqueous. Aqueous. Because they're all aqueous, I'm going to have some water present. And because I have water present, I therefore get reaction of my water. So as you can see here, water is the strongest reductant, and as such is oxidized into O2 gas. So K2+, H+, K+, and H2O can be reduced at the cathode. Cu2+ is the strongest oxidant, and as such is reduced at the CO solid. So, despite the fact you can have these products go through everything, you end up with the H2O and the copper 2+. And now maybe you wanted the copper 2+ to go through it and produce CO solid. But maybe you didn't. Maybe you didn't want this to happen. You didn't want the H2O to go through and form O2 gas. So therefore, you're going to have to consider things like molten mixtures to remove H2O. So especially when we go through electrolysis, H2O is a bit of an issue, and we start to discuss what about molten versus aqueous. Now, this is a good practice question here because it sort of goes through, hey, in an aqueous solution of containing a mixture of this and this, and it was electrolyzed using unreactive electrodes, what is going to happen? What's going to happen at the anode? So I want you to have a go at this question. I want you to pause the video, take yourself a minute or two and have a go. I'm not going to wait. I will just go straight into the answer. That's why I suggest 3, 2, 1, pause. And now hopefully you've had a go at this question. You can come back. So if we look at this question, we've got calcium ions, we've got bromine ions, and we've got potassium ions and iodide ions. So if I go back and I find all these things in here, which I'm not going to bother doing, I would find that, you've got your iodide ions here, bromide ions here. I should be using a different color, but that's okay. I've got potassium ions all the way down here. And what was my other thing? Calcium ions. I don't even think calcium is on here, so it doesn't really matter. I don't think calcium. Oh no, calcium is on here. Calcium's down here. So, strongest oxidant is going to be my calcium. So calcium is going to be reacted. It's going to go through reduction. It's going to be at my cathode. But this question is asking what's happening at the anode. So which of these is my strongest reductant? That is my Ci minus, or my iodide ions going to iodine, and therefore I get my answer being D. So as you can see here, this is a good explanation of it. The answer here is D. So then we go on to discuss exactly what I said before. What about molten versus aqueous? So what about when we have this issue where we've got molten and aqueous solutions? So as you can see here, this is a molten solution. This is a liquid. There is no water present. This has been heated up to a very high temperature to remove all the water, and now we've only got sodium and chloride. What species are present? Well, there's only sodium and chloride. What is the strongest oxidant? Sodium. What is the strongest reductant? Chloride. So what is going to happen? I'm going to form sodium solid, and I'm going to form chlorine ions. Oh, chlorine gas, sorry. Now what about here? Well, now I've actually got H2Os present. So I've got these H2Os present because I am aqueous. So what happens if I go through electrolysis? Well, my strongest oxidant is H2O, and my strongest reductant is also H2O. So I get H2O reacting with H2O, which is completely useless. And that's what happens in these situations here. So water is being preferentially reduced and oxidized in this situation here, and that's not what we want. We want to avoid this pretty much at all costs. So essentially in these situations here, you need to consider the idea that molten versus aqueous needs to occur. When are we going to use molten? When are we going to use aqueous? And why? And that's because water is present on this list. Water is everywhere on this list. These are the two you're going to work with. This one here you can also work with. The issue is it needs to say that oxygen gas is present. If it doesn't state it, then you cannot use this one here. So really important that this one doesn't get used unless it states that oxygen gas is present. As you can see here, you can use this because this is the only thing that's on the left side, and this is the only thing that's on the right side, so you can use these ones because it doesn't need to say if anything else is there. Very good. All right, so another practice question. I think the best way to learn electrolysis is to continue doing practice questions. I find this is probably the strongest and best way you can go about this stuff. So it says here a student is investigating the relationship between the amount of charge used in electrolysis and the mass of metal formed using 3 beakers. And it says here that you've got the student performs an electrolytic reaction and you've got these things here. But how do I determine what is going on here? So this question's actually, I think this question's going to be further back. I do apologize. This question's going to be further back. So this question we'll come back to. This question is actually meant to be at the end of this topic, so we'll come back to it, don't worry. Primary cells. So let's now quickly talk about, before we jump into the math side of things, which is this question here. This is the math side of things and Faraday's laws, and we will talk about this question, don't you worry. If I talk about primary cells, and I talk about secondary cells, what am I talking about? Well, primary cells are essentially non-reusable cells, and these are essentially fuel cells and singular galvanic cells. Now, primary cells have irreversible reactions. You cannot turn them back. You cannot take what was produced and form it back into a fuel or whatever it was that was the reactants initially. Secondary cells, on the other hand, are able to be reused because the electrochemical reaction that occurred in these cells is reversible. So these are made up of galvanic and electrolytic components. So as you can see here, we have a chemical energy, electrolytical energy, we have discharge versus recharge, and secondary cells have discharge and recharge, and it's something that is an important way of distinguishing what is going on in a cell and whether something is a secondary cell. Now, also really important, these are made up of a galvanic component. There was a question, I think it was the 2018 or 2019 exam, VCAR exam. The first multiple choice question was, what is present in both a secondary and a primary cell? And the answer was a galvanic cell. Because a galvanic cell is present in both. In a primary and a secondary cell, a galvanic component is present. It goes through discharge, where it goes from chemical energy to electrical energy, and that process is a galvanic process. That is a galvanic cell. So there is a galvanic cell as part of a primary cell and a secondary cell, and that is a really important wording. So secondary cells must meet specific requirements in order to recharge. So these specific requirements you must be able to recite on an exam. So the products of discharge must exist in a reversible form, and the products of discharge must remain in contact with the electrodes. If one of the products of discharge is a gas, for example, it's not going to be able to be reversible. Why is that? Because the gas just leaves and heads off into the ether. Yes, you can sort of trap it there, but even so, it's not going to be in direct contact with the electrode all the time, and it doesn't work all that well. So gases are generally terrible for secondary cells, so we don't want gases. We generally want solids. Liquids are okay. Solids are better. That's what we sort of say. Now, during recharge, the anode and the cathode flip sides. So what was the anode becomes the cathode. What was the cathode becomes the anode. We then have a flip of charges, which means the charge actually stays the same at each side. So this used to be the cathode and was positive, is now the anode, and you would think negative, but it's actually now positive. So it stays positive on the sides. The anode remains the side of oxidation, the cathode side of reduction. The electrons continue to flow anode to cathode. So this is a really good way of doing this diagram. So I drew this diagram out. It's very simple. I just drew some boxes and a little circuit. As you can see here, you've got your anode, you've got your cathode. And then what happens is that this is in discharge. This is our galvanic component of our secondary cell. We're in discharge. We're producing electricity. Bang. We now become the cathode. We now become the anode. Now notice these half equations haven't flipped over. So they should have flipped over. I do apologize. That's my bad. These should have flipped. So don't worry about these half equations. But essentially these half equations should flip. So essentially you should have this now going the other way. So actually the better way of doing this, and I do apologize, I thought I edited that, but I didn't apparently. The best way of visualizing this, if I get this rubber out and I go, let's go here, and we go, yeah, and I get rid of this and I draw an arrow that way. That is a terrible arrow. This one goes that way. So as you can see, this now has essentially the electrons on the product side, which should be the right side. So this has now become oxidation, which is at the anode and is positive. The electrons have moved to the reactant side, which should essentially be the left side, but essentially these electrons are being gained. So it's reduction, it's at the cathode, but it's now negative. So really important that you do flip this equation. I'm going to make sure I go ahead and I'll edit this before I upload the slides, so you guys have this edited on the slides. I do apologize. This shouldn't be, this should be the other way around. But nonetheless, this is a really good example. When you look at this example here, so that goes like that, and that goes like that. So a really good example of discharge versus recharge, other than the fact I forgot to put those equations. But secondary cells in everyday life are referred to as rechargeable batteries, much like the ones used inside your laptops and phones. However, all these batteries have a lifespan. So why do batteries degrade? This is another thing you need to be able to discuss on an exam. So you need to discuss the idea that if our materials in an electrolytic cell need to stay they need to stay in contact with the electrode. What if you drop your phone and a bit of the material flicks off and can no longer get in contact with the electrode? Well, it can no longer be utilized in the reaction. You've lost a bit of your chemical energy, therefore you have lost a bit of your rechargeability. So loss of active materials from the electrode is a really common example. Formation of crystals on the electrode, reducing the surface. They also increase resistance to flow. So they reduce the surface area available. They increase the resistance to flow. This will degrade the battery. Formation of interfering species by side reaction. So sometimes you get other things in your battery. They form some side reactions, things that we don't exactly want, but we can't really stop happening. This does happen a bit, and therefore you also get some degradation of the battery. And then just things like corrosion and failure of internal components. So essentially battery degradation is really important to understand, that your battery will never be perfect over a long time span. Now, Faraday's laws. So I've jumped back here and said redox basics. The reason I've jumped back here and said redox basics is because Faraday's laws, interestingly, come up as part of Area Study 1 now. So they come up as part of our fuel and our galvanic cells. However, I personally feel like it's more useful in electrolysis, and they do also come up again in electrolysis. Now, there is more detail in the first area study because they want you to be taught the exacts of the Faraday's laws. The area study 2 Faraday's laws dot points are more about the application of it. So I actually personally feel like they're still emphasizing area study 2 and the use of Faraday's laws in electrolysis, which is what I'm actually going to teach more of today. However, the idea is that you should know how to look at Faraday's laws when it comes to cells and redox basics, which is part of area study 1. So if your sacs are split up into area study 1, area study 2, and you have redox split up from electrolysis, then you do need to know Faraday's laws for that first sac. If they're not split up, doesn't matter. You're going to learn it no matter what, so don't stress too much. But there are 2 major Faraday's laws, and you do need to know both of Faraday's laws. So Faraday's laws are essentially, the first one is that the mass of the metal produced at the cathode is directly proportional to the quantity of electricity passed through the cell. So if you pass more electricity through, you get more metal produced. If you get less electricity passed through, you get less metal produced. And for 1 mole of substance to be deposited at the cathode, a whole number of moles of electrons is required. And this is where our 96,500 sort of constant comes from. Also, as you can see there, Faraday's also has a constant. It's equal to 96,500 coulombs per mole. We'll utilize our formula to link all these concepts together. Now, there are 2 major Faraday's laws. The first implies the mass of the metal is sort of determined by the electrical sort of activity. But when he wrote this out, he said like the mass of the metal is proportional to Q. And what does Q mean? Well, Q is the charge in coulombs. So Q is coulombs, I and T are amps and seconds in time. So we do know a very similar equation to this, which we talked about earlier. A very similar equation to this, which we talked about in the last area study, which was calorimetry. So we would have discussed this in calorimetry. We would have discussed E equals VIT. That was in area study 1 with like our foods and our fuels as foods. Here we look at Q equals IT. So slightly different, but very, very similar. But again, how does this relate to mass? So you've got Q equals IT. How do I relate this back to mass? What am I going to talk about with mass and metal? Not really sure what's going on. Well, we can determine the moles of electrons from charge. And so the moles of electron is equal to the charge over Faraday's constant. And if we know the moles of electrons, we can then utilize that to determine the moles of a product, like our solid nickel here. We can then determine using stoichiometric ratios and stoichiometry what is our mass of our nickel. So these 2 equations need to be used in sort of a flow chart path. So you need to know Q equals I times T, and N, or moles of electrons, is equal to Q over F. And F is your Faraday's constant. You'll find this in your data booklet, but you're also welcome to just remember it. It's something you should just remember. 96,500. Charges in coulombs, and that's probably about it from there. This is essentially what your pathway looks like. So you can either go this way or you can go this way. And it's really important that you understand you can go both ways in these questions. You can start with a mass of fuel and determine the amount of charge that, or It doesn't even need to be massive fuel. It should be really massive metal, to be honest. I think I sort of got this from... So realistically, what we talk about here is that we can talk about this in terms of our air study 1 with fuels, but realistically, I want to talk about electrolysis. So we'll talk about metal. You can get your mass of metal and determine how much charge was given, or you can determine the amount of charge that was given and the mass of metal that was deposited. So you can kind of go one way or the other with this, and it's important to understand that it can go both ways. This is not just a one-way pathway. You need to know both ways. You need to know left to right, and you need to know right to left. You cannot just think it's always going to go one way. So as he says, this pathway can go forward and backwards. So super important you practice this both ways. Now, what is an actual practical example of this? And the reason why I think it's more relevant to understand Faraday's in context with electrolysis is because the application for it is much broad, is far more broader. I think there is far more examples, or many more examples. I don't even know how you want me to Englishly say that. Terrible English of mine. There's just a larger breadth that you can get to with electrolysis. And one of those examples is electroplating. Now, I hope some of you have seen electroplating before. This was essentially, it is discussed in Year 11, Unit 1-2. So very, very briefly, it's not discussed in detail though, because you don't go through really electrolysis in Year 11. But electrolysis is essentially the idea that, or electroplating, sorry, is the idea that if you take an object, such as a spoon, and you want to put a thin layer of silver over the top of it to make it look like a fancy spoon, you can put it in a solution, apply a battery, and then you can sort of suck what you want out of that solution onto that spoon. Now, this is essentially what it looks like. So if I want to take this electrode here, so I've got two electrodes. I've got a gold electrode here, and I've got a copper electrode here. Now, let's say this copper electrode is something. Let's say this copper electrode is a piece of jewelry. I don't know why you have copper jewelry, but let's just say it is. You've got a piece of jewelry here, and you've got a big wad of gold here. And I essentially want to cover this copper jewelry in a thin layer of gold so it looks really fancy. That's what I want to do. The best way to do this is via electroplating, where you put your gold here at your positive anode. So this is your positive anode. This is your negative cathodes. These electrodes, once we start, this will be positive anode, negative electrode, negative cathode. And what we do is this. So when we start the battery, all this stuff going on, you get your gold breaking down. So this gold breaks down into gold ions and electrons. Over at your cathode, you suck these gold ions out of the solution and onto the surface of the electrode, which in this case here is a metal. It is the copper jewelry. And you suck it onto there and you sort of attach it as a thin layer and you form gold solid. So as you can see here, electron comes off, gold comes out. Gold becomes a gold ion. That becomes smaller, as you can see there. The electron goes down. The gold attaches on with the electron and becomes gold solid. And then that starts to become bigger. And essentially all it's doing is getting a big gold layer on the outside. That is electroplating. That is electroplating at its finest, and that is essentially how it works. And the most common example of this is like silver plating of like spoons and tin plating of cans. You also get like copper plating of things. Electroplating is a really useful tool. Now, there is also electrorefining. I'm not going to discuss electrorefining today. I think it's probably the next step on, and we don't really have enough time to discuss it. But the other really good example of Faraday's laws and electrolysis is electroplating, and something that you should really look at discussing. Now, in this situation here, going back to electroplating, if I wanted to make it a really thick layer, I'm going to need to apply more electricity for a longer amount of time, as per my equation back here. This equation, I'd need to apply over a longer period of time, and I'd end up applying more charge overall, or I could increase the current, either. So if you increase both the current and the time, I'm going to increase my Q even more. And then when I increase my Q, I increase my moles of electrons, because my Q gets larger, gets divided by the same amount, but it's going to end up as a larger value. I end up with more moles of electrons more moles of electrons when I use stoichiometry is more moles of my metal, and therefore more mass of my metal. So naturally, that's what's happening there. Let's jump through. All right, so what are the factors affecting the metal that is deposited? I don't want it to be over here, but it's obviously too big. So what are the factors affecting the metal that is deposited? Well, first of all, there's the charge of iron involved in the reaction. So if you look at here, nickel, to make a nickel solid atom from nickel ions, I need 2 electrons, whereas silver, I only need 1 electron. So nickel is going to require twice as many electrons as silver. So it's going to take longer to essentially get the same amount of metal deposited in moles. The current flowing through the cell, we discussed already. If we increase the current, we're going to get more electrons, because current is essentially a measure of the rate of electrons. So if we increase the current, we get more electrons. More electrons means more metal being deposited, and a higher current means, essentially more electrons are delivered. And then our last factor is the length of time. So if the time is increased, the longer the current flows, the more electrons are delivered, the more metal is deposited. So all these sort of simple facts can assist you in determining what is going on. Now I do apologize, my Mac is going a little bit flat, so hopefully that'll charge now. So here's a really good example of Faraday's in an exam or in a question-based setting. So a company needs to produce 25 grams of silver to create enough jewelry to sell its clients. To do this, they set up an electrolytic cell with the following half reaction occurring at the cathode. They run this cell using a current of 5 amps for 2 hours. Would the company have produced enough silver? So you're welcome to have a go at this question if you would like. I'm going to go through it. If you have no idea what's going on, please feel free to just stick with me and we'll go through it. If you want to challenge yourself, please do pause right now and have a go at this question. Use the equations we've just been through. So Q equals IT, our our moles of electrons equals Q over F, which is 96,500. And have a go at this question here and see if you can determine what is going on. So have a pause now. 3, 2, 1, pause. And hopefully you're back. All those who stuck with me are still here. Let's go through this. So first step, we can determine our coulombs or our charge because we've got amps and we've got time. So 2 hours of time is essentially 2 by 60 by 60. So I do 5 by 2 by 60 by 60 and I get 36,000 coulombs. I then determine my moles of electrons by going 36,000 divided by 96,500, which gives me 0.373 moles. Now, it's a 1-to-1 ratio from this to this, 1-to-1 ratio from here to here. Therefore, my moles of silver deposited is also 0.373. And then I say, all right, well, what is my mass? Well, it's going to be 0.373 times by 107.9, and I get this answer here. So I get 40.25 grams, and I would say, yes, they would have been enough. So 40.25 grams is more than 25 grams, therefore they would have enough silver. So essentially, I've got my answer and I've answered the question. If I didn't write yes, they would have enough, or probably saying they would have enough silver is probably the way you want to write it. You want to completeness sake, you want to put silver at the end there. But if I hadn't put that down on the page, I'm not getting the answer there. I haven't done that right. It's really important. So notice in that example, the silver had a 1-to-1 ratio to the moles of electrons. What if we utilized a metal such as copper? And we've already discussed this. These moles, the number of electrons, you're going to need double the electrons. So as copper has a 2-to-1 ratio, meaning the moles of copper produced from the same number of electrons would be half, I need to understand that this diagram here is really useful. It's going to come up, it comes up a lot. This graph shows that through Faraday's second law, we can visualize that if I apply the same charge over, I apply the same current at the same amount of time, so I apply the same charge, if I have silver, I'm going to get more moles deposited than if I had copper. So if I applied 3 Faraday, so if I applied 289,000 charge or coulombs of charge, I'll get 1 mole of chromium for every 3 moles of silver. So I'm going to get 3 moles of silver. It's actually like down here, and that would be equal to 3. Let's just say that there would be 3. So I'm going to get 2 if I was down here. I get 1 if I was here. So as you can see, I get 1 of chromium at 3 Faradays of charge. So I'm not getting nearly as much. So understanding that there, if I come back to this question from earlier that was out of place, this question was meant to be now. I have this question here where a student is investigating the relationship between the amount of charge used in electrolysis and the mass of metal formed using 3 separate beakers pictured below. The student performs an electrolytic reaction to each beaker using a current of 2.4 amps for 10 minutes on each. The change in mass of each cathode is then accurately determined in order from least to most. The mass of each metal formed in the cathode would be, so least to most. Which one's going to form the least? Which one's going to form the most? Well, the easiest thing to understand, first of all, is looking at, all right, I have +1, I've got +3, and I've got +2. So to form essentially a solid here, I need 3 electrons. Here, I need 1 electron. Here, I need 2 electrons. So the mass of each metal from least to most is going to go this one, then this one, then this one. So that's that idea that we've just discussed then. So really important that we understand that from this diagram up here. So this here is another really good question. This is looking at a electrorefining, but this is still a very doable question, even if you don't understand electrorefining. In this question here, we've got electrode 1 is a blister copper. Now, the blister copper is made up of a bunch of things. It's got zinc, cobalt, silver, gold, nickel, and iron. As you can see here, electrode 2 is pure copper, and pure copper is being deposited at this electrode. You can see this diagram here. It says, which of the following shows both the equation for the reaction occurring at the cathode and the polarity of electrode 1? So, have a think. I'm getting copper deposited here. I'm getting copper deposited here. What is happening? And then electrode 1, what is my charge? So, take a minute, have a think. Pause if you need. 3, 2, 1. And hopefully you're back. So, if you had to go at this question, the best way of going through it, you could have read through it multiple times and had to think about it. The best way to think about it is, well, copper's being deposited here, and I know it's copper 2. So, therefore, I'm going from Cu2 plus, this is a terrible Cu2 plus, I'm doing this on my mouse, Cu2 plus, I'm going from Cu2 plus 2E minus to copper solid. So I know that's what's happening at this electrode here. It says there is pure copper being deposited. I know it's a little bit cut off, but that is literally what's happening. It's telling me there's pure copper being deposited. So when there's pure copper being deposited, I know that my cathode is going to have to be this, because this is a reduction equation. So therefore, my cathode has to be A or C. So B and D are gone. Straight away, B and D are gone. So then it's either positive or negative. Well, if I know that this is my cathode, and therefore I know this is electrolysis, so therefore this needs to be negative, therefore this side has to be the anode and has to be positive. So therefore electrode 1 is positive, and your answer here is A. And that's a simple way of going through that question. All right, so if you need another break, please feel free to go take one. We've got about 30-35 minutes left to punch through reaction rates and a little bit of equilibrize. We're not going to get through all of equilibrize. We're going to very briefly look at equilibrize. Reaction rates is also very quick. It's only about, what is it, about 1, 2, 3, 4, 5, 6, 7, 8, it's 9 slides, and then equilibrize we're going through in less than 20 slides, which is not the whole grouping of equilibria. It's a very short amount of equilibria. So if you need a break, please feel free to pause and go have a break. Otherwise, we're just going to punch through this last sort of half an hour. All right, so reaction rates. So rates and equilibria is really sort of a really cool topic, because it's the first half of unit, or I wouldn't even say it's the first half, I'd say it's the first 3/4 of Unit 3 Area Study 2. And it can sort of be split up. It can be split up into reaction rates, which make up about, I don't know, about 20% of this. I'm in the wrong part, here we go. These make up about 20%. That is a terrible 2. I don't know why that's so bad. It makes up about 20%. That's a better 2. This makes up about 80%. And when I say 20%, it's 20% of the 75%, and this is 80% of the 75%. So as much as we're going to spend probably about equal amounts of time on both of these today, this is worth a lot less. So this side of things here is worth a lot less than this side of things. It's just that today what we're going to do is we're going to discuss this sort of 80%. We're going to discuss that sort of, we're going to discuss that very briefly because essentially I don't want to sort of overdo it today. We've gone through heaps of electrolysis, heaps of redox, so we're just going to very briefly look at this stuff. All right, so reaction rates. Let's start off. So what are rates of reaction? So rates of reaction essentially discuss or describe how quickly a reaction occurs. And essentially we do this using collision theory. So what is collision theory? So collision theory is this idea that chemical reactions are a result of collisions between molecules, but not all collisions equal a reaction. And that's a really important idea, that for a reaction to occur, there are certain things that must happen. And when a reaction does occur between a collision, we call that a fruitful collision or a fruitful reaction. The two main aspects are that a collision must have sufficient energy and the collision must occur in the correct orientation. And you need to know those two ideas. So to have sufficient energy, the reaction must have more energy than the activation energy. So this diagram here, I made this diagram on PowerPoint. So it's by PowerPoint, a very nice PowerPoint diagram. But as you can see here, you've got your reactants and you've got your products. You've got your activation energy and you've got your delta H. Really important, for a reaction to occur, there must, when the reactions hit each other, it must produce more than this amount of energy. If there's not more than this, if it doesn't get to, like, let's say here, which is above it, if it doesn't get to here, it's not going to happen. This is the minimal amount of energy it needs to get to for this reaction to occur. It needs to be above it. So it needs to go up, 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 up. It needs to get above this line, and therefore it will then do the reaction. So the activation energy can be referred to as either A, and the energy, this is the energy needed from ground state to transition state. So it's transition state up here. Can be described as an activation barrier. We call activation energy. Reactions with a greater temperature have a greater kinetic energy and therefore more likely to get above your activation energy. So those with a higher temperature have greater kinetic energy and are more likely to be able to jump above that activation energy. That's why sort of warm mixtures are sort of easier to work with in terms of reactions. So as you can see here, energy of collision is greater than activation energy. That's stuff you sort of need to know. So collisions must occur with correct orientation is the second idea. So first of all, you need enough energy. And if there's not enough energy, it doesn't matter if it's correct orientation or not. That's just too bad. So let's say we've got enough energy. Now we need to hit this in the correct orientation. It's like pieces of Lego. They have to go one on top of the other. Can't be putting, backs on backs, ends on ends. They're not going to go together. It's the same sort of thing with chemistry. You need to have the correct things locking onto each other for a reaction to occur. So collisions must occur with correct orientation for the reaction to succeed or be fruitful. This is like a door with a push-pull sign. Obviously, you can't pull a door that says push. I do that all the time. But this is a diagram that was actually done by one of the last tutors that was running this, Jack. And I've sort of kept reusing it because it's a really good diagram. But as you can see here, it shows that whole idea of where this OH needs to connect in a certain spot. It needs to be essentially, it can't hit in the same spot of where what it's knocking off is. It needs to essentially hit the back end and knock off something at the front. And as you can see here, if I added it directly on, it's not going to react. It can't do that. So you need to be able to sort of like push it from behind in a sense. And that's how you end up with this reaction. The whole specifics of correct orientation is probably a little bit beyond the scope of VCE, if I'm blatantly honest. You really just need to be able to mention the correct orientation and that sufficient energy above the activation energy is required for a reaction to occur, and this is what we refer to as collision theory. That is essentially what you need to know for it. Now, what are the two fundamental ways to increase reaction rate? So then we start to talk about, hey, reaction rate, we've talked about correct orientation, we've talked about sufficient energy. Now, what about increasing our reaction rate? And there are two approaches to this. So what are our two approaches to increasing reaction rate? Because we want things to go fast. It's reality. We don't want things to go slow. We want things to go fast. So method one is to increase the collision frequency. And we can do that through three different things. Increase the temperature, increase the pressure/concentration, or increase the surface area. Method two is to increase the proportion of successful collisions. So a high temperature or a catalyst, and that's the best way to go about it. So really important, you need to know these two things here. You need to be able to apply those two things there and you'll be fine. So you'll smash them out if you do those two things. So collision frequency. First of all, you need to increase the temperature. So if you've got a high temperature, you've got a faster movement of particles, you've got a higher collision frequency. That higher frequency of successful and fruitful collisions means you get a higher reaction rate. That's eventually the essential way you go about it. What about if I increase my concentration or my pressures? Well, in doing that, you'll have more particles. More particles means more collisions, equals more successful collisions, equals higher reaction rate. If I increase the surface area, same sort of concept. You've got a higher surface area, you've got more stuff to bump into, you've got a higher collision frequency, more successful collisions, higher reaction rate. So very similar pathways, just slightly different. What about an increase in temperature for proportion of successful collisions? So really important, temperature does both, and it's the one you need to know that does both. A higher temperature, faster moving particles. Faster moving particles essentially have more kinetic energy. More kinetic energy means more collisions that overcome the activation energy. Increasing the temperature affects the reaction rate in both ways. So important that you get both ways, you get an increase of activation energy. Use of a catalyst. So a catalyst provides an alternative reaction pathway with a lower activation energy. This then allows for more collisions to succeed. It's really important you know that wording and that specific wording. Catalysts provide an alternative reaction pathway with a lower activation energy. This allows for more collisions to succeed, and therefore you get that whole idea that it's the alternative reaction pathway. So that is like, we must know wording for Saxon exams. If you don't display that wording in Saxon exams, then you will be knocked down for marks. You won't get marks, and that's really important. You need to be able to apply that wording. Without that wording, things are not going to be right. So really important. So as you can see here, this is an example of what it looks like when you lower the activation energy. So you have your reactants here. This is your normal activation energy. You apply a catalyst and it lowers the activation energy. So this is the minimum amount of energy you now need. And it goes through this pathway, and essentially you still get the same delta H here to here, or as you can see through this arrow here. That's terrible. It should be there to there. You know what I mean. It's terrible arrow, but it does the job. So that is essentially how you increase your reaction rates. And that is all you really need to know for reaction rates. The only other thing with reaction rates that sort of leans onto equilibria is this idea of what about rate versus extent? Well, rate, we just discussed, is how fast things go, and we want to increase the speed. What about in terms of equilibrium? How fast does it reach equilibrium? Well, reaction rates are going to increase how fast we reach equilibrium, but it's not going to change where the equilibrium is. Extent is how far the reaction has gone, or where the equilibrium is. So extent is all about where the equilibrium is, and how much reactant has been converted to product, or vice versa. So equilibrium is all about extent, and being able to distinguish these two words is another important skill you will need to apply when you go into VCAR SACs, VCAR exams, or VCE Chemistry. So let's jump in. We've got about 18 slides of equilibria to go. So let's smash through these. Now, at equilibrium, we discussed the idea that the forward and back reaction are cancelling each other out. And that's essentially what equilibrium is. We're in a nice area where everything is staying the same. Now, it's really important to understand that the forward and back reaction are still moving. They're still going forward and back. You've still got the forward reaction going that way and the back reaction going that way. We refer to this as dynamic. So dynamic equilibrium. And this is a really good diagram of it. As you can see here, we've still got movement. We've still got products becoming reactants, and we've still got reactants becoming products. But we don't observe a change. We don't observe a change. We don't observe any difference here. We cannot see a difference because it's all happening at the same rate. So the forward and back reactions are occurring at the exact same rate, and therefore we are at what we refer to as a dynamic equilibrium. So when we reach equilibrium, concentrations become constant. Reaction rates remain the same. And that's really, really, really important. So equilibrium works off extent, as we just said. We need a good way to display how far the reaction goes. We can quantify the reaction extent via a K value, which we will discuss. We'll get to a K value in a bit. We're not going to discuss that right now. But we can also sort of look at it through concentration time and rate time graphs. And these you do need to know a lot of detail of. We're not going to go through them in super detail today. You do need to know how to manipulate them in terms of Le Chatelier's principle. So you do need to know how to draw out a concentration time graph where something has been removed, and therefore we have then had a partial opposition to the change, and we've tried to go back to equilibrium. You do need to know how to do that. It is important. It's an important skill. We're not going to discuss it today. But what do these look like? So if you've never seen these before, this is a rate versus time graph when we're reaching equilibrium. Where have we reached equilibrium? We've reached it right here. So this is where we reached equilibrium. As you can see, the forward and back reaction are now on top of each other. You can't really see them. They've merged together, and you've got forward and back at the same rate. So the forward reaction is going this way. Back reaction is going this way. From this graph, I can tell you that we started with this and this. How do I know that? Because the forward reaction started off really high. Therefore, that tells me that initially we had lots of O2 and lots of SO2. Eventually, as some SO3 formed, the SO3 started to bump up against each other and react back into SO2 and O2. And that's where we slowly got this increase in back reaction. And eventually these two met in the middle, and now they're constantly at the same rate. The concentrations will look the same. Now, what about the concentration time graph? Well, it just confirms what I just said. I said that we had no SO3 at the start, as you can see here, and we had an amount of SO2 and we had an amount of O2. Now, at equilibrium is probably about here. I'm assuming it's where that line in that thing is, where I haven't made the lines perfectly match up, but I'm assuming equilibrium is reached about here. So it should be at the same time as this graph here. It's probably not perfect, but it's meant to be at the same time as the rate time graph. Essentially, you've had these two. Essentially, you've had these three lines here. Now, the SO2 has a 2 out the front. The O2 has essentially a 1 out the front. If I got like a measuring device out, if I got a ruler out or something, and I put it on my screen, now I'm not going to do that, but use a different color. Let's use green. If I measured, oh, that's terrible. We are going to rub that out. Let's try that again. Let's try that again. That's a little bit better. It's not amazing, it's better. So if I measured this distance here and I compared it with, now I'm going to choose another different color of green. If I compared it with, that is terrible. That should be way higher. Let me redo that. All right, we're only getting 2 opportunities to do this because I'm not going to waste time, but I will try it again just because I think that was terrible. Oh, that was terrible. I shouldn't have dipped down there. But anyway, imagine that's a straight line out. And if I compared it with this distance here, this should be 2 times this distance here. And this should be just like 1 times. Because this has a 2 out the front and this has a 1 out the front. So this should be 2 times the distance. This should have reduced by 2 times the concentration of the O2. That's a really important thing. Therefore, the SO3, if I measure this distance here, this distance should be the same as this distance. These two should be the same distances. It should be 2 times the distance of reduction in the O2. So you've got to look at your coefficients at the front of your equation. That's how you determine how much concentration reduction or increase you're getting. Again, another important skill. So as you can see, equilibrium reached. Oh, I've even done it. So I didn't even need to waste my time doing that. I was nice enough to do it myself. I thought about myself beforehand, and then I forgot that I did that. So let's go and do this, because I definitely thought about myself when I was making these slides, and when you are going to dislike drawing this out. All right, let's have a look. So 1 unit increase. So increase and decrease to equilibrium occur at molar ratios according to the chemical reaction. So the increase here would also be a 2 unit increase. So both of these would be the same, essentially, unit increase / decrease. So knowing the exact concentration of components of an equilibrium system can be extremely useful. But in some cases, you may not know all the values, and you need to figure out what the rest are. So in this case, we determine them by using what we call an ice table. So an ice table can be utilized in both moles and molar concentration form, although the latter is more useful. So using molar concentration is more useful, but moles is fine. You can use either. So as you can see here, we're going to use this one in moles. We're not going to use molar concentration here. Oh no, this is molar concentration, sorry. So we're going to use molar concentration here, but you can use moles. Molar concentration is more useful. So as you can see here, we've got an equation. It's 2A plus B goes to and comes back to C. So this is a double arrow, so it says we've got an equilibrium system. At the beginning, we add 3 moles solution of A and a 1 mole solution of B. So we've got 3 moles of this, 1 mole of this. At the end, we measure 1 mole of A. The rest is unknown. So this is essentially what my diagram looks like at the moment. This is essentially what it should look like. This is what my ice table should look like. Ice table, initial, change, equilibrium, ice. This is my ice table. Let's start to fill it out. Well, initially I know I didn't add any C. So if it doesn't mention adding C, I assume 0. I assume nothing was added. I know that I had a 2 mole decrease here because I went from 3 to 1. And given that this is 2x, because this is a 2 out the front and these are 1s out the front, I know that these two must be -1 for B because it's on the same side, and +1 for C because it's on the other side. Therefore, I should have 0 and I should have 1. And that is what my end concentrations are. So here's one for you to have a go at. So I've already filled in what you need to know on the ice table. I want you all to have a go at this now and see how you go. So this shouldn't take very long. This should take you no more than a minute or two. I haven't even made a question for this. I've simply just given you an ice table with some values already put on the screen, and you just need to fill in the blanks. That's all you need to do here is just go ahead and fill in the blanks. So have a go at this. 3, 2, 1, pause. And hopefully you're back. So hopefully you had a go at this one and you didn't have too many issues, and I assume you shouldn't really have any issues with this stuff. So as you can see here, you should have just input different values into the screen. So as you can see, you should have had, this was negative, so this is also going to be negative. They're both 1s, so cool, don't need to change it. This is also a 1, but you're going to add it, so therefore you then do the maths. Very simple. You have your calculator in there, so feel free to use your calculator. This shouldn't take you very long. So I've already input all the values for you. This is the sort of question that shouldn't take you more than, as I said, I gave you 2 or 3 minutes realistically, but I think you should only be using 1. Pretty straightforward sort of stuff. So now that we have these values from our ice table, where can we use them? Well, we can use them in our equilibrium constant, which is K. Now, our equilibrium constant, as we discussed earlier on, is our statistical measure of how far our equilibrium system goes to one side. So it goes to the reactants or the products. How far does it go? Or realistically, it's just discussing where it is on the spectrum. So when we discuss this, we use a K value, and our K value is determined with this nice little equation here. You need to know this equation. You need to write this equation down whenever you use it. And I mean that. I mean you will write this equation down every time you use it. This does not mean you're going to write K equals C, D, A, B. You are going to write what is given in your equation. So if you're on that last one here, you would be writing K equals, and then you would be doing I3. So you'd be doing I3. So I can probably do this. It's not going to be very nice, but we'll do it to the best of my ability. So this is going to be I3. Now there is no coefficient, so I'm not going to have any power. There's no coefficients at all in this, so there's going to be no powers, which is a little bit boring. I would then do I2 underneath, multiplied by I negative. And this should have been negative up here as well. That I would write down. Even if I'm going to do this calculation and I'm going to do it on my calculator, I'm going to write this down first. This is where one of my marks is. You must always, always, always write down your equation for your K value. So as you can see here, I will write down my K value all the time. And this is what your K value looks like. Your coefficients go as powers and your values go in as concentrations. So that's why we talk about concentrations being more useful in your ICE table, because these are all concentration. Square brackets means concentrations. So concentrations are a lot easier to work with, and they're the smarter thing to work with, so that's why we talk about concentrations here. So as you can see here, A equim means the concentration of A at equilibrium, so on. K values describe the extent. A large K value will have lots of products. A small K value will have not a lot of products, which means a large K value tells you that the extent is very much to the right. I've got lots of products. A small K value tells you I'm very much to the left. I've got lots of reactants. So as you can see here, an example, in this one here, I've got a really small K value, tells me I have lots of this, whereas if I have a really big K value, which is 22, I'm going to have a lot of my products. So essentially, these are two different examples where, hey, I've got lots of my acid here, whereas on my other hand, I've got lots of my sort of deionized sort of acid there in my second example. So what if we wanted to change the K value? How will we go about it? So if I wanted to change the K value, it's really interesting. They are associated with chemical equations. So this means no matter how much you add the product of the products and reactants, if they form the same chemical equation for equilibrium, the K value will be the same. So no matter how much you add of everything, the K value will be the same for the same chemical reaction. The K value only depends on temperature. Temperature is the only thing that plays around with the K system. As per why in this last one, I had 25 degrees next to them. Temperature is the only thing that changes it. Now, you can manipulate your K value if you manipulate your equation. So what if I wanted to reverse my K value? Well, if I wanted to put 1 over my K value, I need to reverse my equation. So if you see here, I go A plus B goes to C plus D. That's my K value. Well, if I do C plus D goes to A plus B. So I flipped it. I essentially flip what goes on top and the bottom. So I get 1 over K1. Same thing here. If I want to double my equation, if I double on my coefficient, I'm essentially just going to put my K value to the power of. So these are different equations now. That's why I said temperature is the only thing that can manipulate a K value of the same equation. These are all different equations. So therefore their K values in a sense are different only if we manipulate the full equation. As you can see here, if we add equations, we get a different K value again. So we go K1 times K2. So I've added these equations together. When I add them together, I multiply K values. So then what about the reactant quotient? So the reaction quotient describes where the reaction is in regards to equilibrium. So if you think about the relationship of like time reaches infinity, you say Q reaches K. So as time goes longer, Q gets closer to K. So essentially, as you can see here, this is an experiment where we utilize nitrogen and hydrogen gas to make NH3 gas. Over time, if I started with nitrogen and hydrogen, and I didn't start with any NH3, over, let's just say these are minute intervals, I measure, and every single time I measure, if this Q value is the same over two intervals, this is now a K value. So these here are now K values. These are Q values. Now, Q values that are smaller than your K value tell you that you need to shift your reaction to the right. Q values that are larger than your K value tell you you need to shift your reaction to the left, as per this slide here. So if Q is greater than K, so Q is bigger than K, the reaction needs to shift to the left. You need more reactants. If Q is less than K, you need to shift to the right. You need more products. So if Q is smaller than K, you need more products. So the Q values are calculated the exact same way as K values. They are just essentially the equilibrium constant when we are not at equilibrium. So this is a really, really good question. I'm going to give you all a second to have a think about it. Essentially, it reads the concentration of reactants and products were studied at the following reaction. So we've got H2 gas, F2 gas goes to 2HF, and the K value is 313 at 25 degrees. In an experiment, the initial concentrations of gas were this, this, and this. When the reaction reaches equilibrium at 25 degrees Celsius, the concentration of HF will be what? So have a go at this one here, and then come back. So 3, 2, 1, pause, and now hopefully back. So in this question here, now I don't have the answers up in front of me, so let me do some calculations. So in this question here, you've been told that the K value is 313. Now, in this question here, importantly, you'd write out your K value, you write out your K. This is a multiple choice question. It was a really poorly answered. That's why I put this here. It's one that stumps students every year. I would find, in this question here, I'm actually not going to find that. I'm going to find my Q value. So I'm going to find my Q value with all these three values. And when I find my Q value with these three values, I go 0.4 times 0.4. So I get 0.16. And I go 0.02 by 0.01. And I get 0.00002. Don't know if that's right. Let me do that again. Yep. So I get 0.0002 underneath. So I go 0.16 divided by 0.0002 underneath. And I get a value of 800. So my Q value is 800. Now my Q value is greater than my K value. So remembering back to that last slide, what does that mean? Q is greater than K. It means I need to shift to the left. So if I need to shift to the left, I need to go this way. So what's going to happen to my HF, which was 400 or 0.4, it's going to be reduced. So it's going to end up less than 0.4 molar because I need to go back to the left. So this is a really good question. Might be a little bit too far advanced if you haven't been through this topic yet, but don't stress if you haven't. All right, and then lastly, you do need to know Le Chatelier's principle. We're not going to discuss it today, but essentially you do need to know how to utilize it in terms of adding, removing, changing, all that sort of stuff. Remember that Le Chatelier's principle is essentially describing that if you do apply a change to the system, an equilibrium system, it will attempt to partially oppose the change to reach equilibrium again. And then there's another really good short answer question here. Now this question here discusses the idea that in a closed vessel, the nitrogen dioxide exists at equilibrium. And essentially you've got a brown versus a colorless. At 25 degrees, you add 0.5 mole of this into a 25 ml flask. So you're adding brown into the flask. The flask is left until equilibrium is reached. At equilibrium, it is found that there's a lot less of this and a lot more of this. Now, if the reaction is then heated, given the forward reaction is exothermic, so you assume this is exothermic, what is going to happen? Well, in these questions here, and I'm not going to go through it in super detail because we haven't discussed it, you need to give this statement here. This is my one tip. Much as we're not going to go through Le Chatelier's principle, if you are going to discuss a question that refers to Le Chatelier's principle, you need to say at the start of your question, according to Le Chatelier's principle. It's like the number one rule with these questions to ensure that you get the mark. So you need to say, according to Le Chatelier's principle, and then you actually need to mention it. You need to say, look, we want to oppose the addition or partially oppose the addition. And then when you reach new equilibrium, yada, yada, yada. So you need to discuss things about the opposition of what you have done. So if you've changed the system, Le Chatelier's principle says that you are going to oppose that change. And it's important that you do discuss that. So that's about it for today. I don't think we want to add any more. I think we've discussed enough. We've gone for about 1 hour and 55, nearly 2 hours. So we've discussed a lot. Essentially from today, I really want you to take out of it that redox is really difficult and that it's going to take time. So please don't feel bad if you've been doing redox and you're really struggling with it. It's just not getting any easier. That is okay. Redox is not fun and it takes time. Equilibriums, we very much went through the basics. We went through all the reaction rates. We very much went through the basics of equilibrium. It is a much bigger topic with lots of little niche things, but it's pretty straightforward. It follows a nice little path, and it's something you can sort of spend a bit of time on and learn pretty well. Other than that, I hope the rest of the year goes well. You'll probably be seeing me around. I'll probably run the rest of these lectures for the rest of the year for chemistry. For those of you who are not watching this at the premiere, please feel free to utilize and read through the chat. I will have answered lots of questions if it was me there. I'm not 100% sure if it'll be me there. It might be someone else. But the tutor that is there will be a very good chemistry tutor and they will have answered lots of questions. So please feel free to use that chat to look at if the question you have has been already asked, because it may already be answered. Otherwise, good luck, and I'll be seeing you around.